So welcome to the 2019 Crypto Inventory Day. So what are we trying to do today? So we're trying to go really from top to bottom on the subject of crypto inventory, starting off with what is it and why would you even want to do it at all? I think from understanding better the motivations, the sort of business reasons why you might want to have a crypto inventory, that'll give us the guidance to answer later better some of the more technical questions about how we should do it or what should actually be in there, to make sure that it's really responding to a need rather than just a kind of technical exercise in itself. The idea is also, of course, to exchange experiences. So as we've just had from our go-around, we know that some of us are more advanced with our projects than others, but I think there's definitely some potential to share some experiences and best practices that we've already discovered in that area. And then we're going to have our invited speaker who's going to talk to us a little bit more about future cryptography, so particular TLS 1.3, but also some stuff around fully homomorphic encryption and other topics. Okay, so quick recap on the program. So this morning we'll do very quickly try and come up with some kind of definition about what is a crypto inventory, and then look into why we might want to build it. So a series of different kind of angles that might be the motivation for doing that work. And then we'll do a little bit more, we're going to sort of drill down through the day. So the second session will be about setting objectives and a scope and data models. So what should really be in there and how would we define those things? And then in the afternoon, we'll look about how we would actually collect that information. So topics like automation, moving that up to scale, how to deal with third-party technologies, this kind of stuff. And then at the end of the afternoon, after the scientific talk, we'll go into some specific topics that, particularly these are things which came up from people when we asked around people who were coming, what kind of topics would you like to look at? Things like crypto agility, so how to prepare for changing my cryptography, and how to manage crypto inventory once we move to public cloud services. So let's start with some definitions. So what is a crypto inventory? So here I've put a series of different answers to the question. So in the most sort of physical way, a crypto inventory is some kind of map of all the cryptography that you use in your organization, right? So it's some sort of list or plan, or it's just an explanation what cryptography you have and what you're doing with it. But there are other ways to view a crypto inventory. So you can also think of it as a strategic asset for your cybersecurity policy. So mostly, there's been a lot of advance in recent years around the idea of inventory being part of a cybersecurity strategy. Years ago, you used to hear that there'd been a compromise on a server somewhere, and you're like, I didn't even realize we had a server in that country or whatever it was. And so a lot of technology has come out and practices have come out around saying, let's manage an up-to-date inventory, and there are a lot of good technologies for this now, so we always know what we have. So you can see crypto inventory as an extension of that, in fact. So if you don't come at it from a crypto angle, but you come at it more from a strategy, IT, inventory management angle, you're just trying to add to your inventory some more information that's relevant to your risk posture, particularly around cryptography. Another way to look at it is a tool for policy enforcement. So most of the financial services and other organizations that we talk to already have a cryptographic policy, and many have had a cryptography policy for many years. It's something that as soon as people started using cryptography more with the sort of explosion of the internet and online banking and so on, very quickly people laid down an idea about, okay, well, these are the algorithms we're going to use, these are the key lengths we're going to use. We want things to be managed in this particular way. But in a lot of cases, these policies were only sort of enforced maybe by kind of occasional manual checks or some sort of self-reporting. Development teams were aware that they existed, these guidelines. Maybe they looked at them, maybe they didn't, but that they were sort of around. And so another way to look at inventory is to say it's a way to make sure that my cryptographic policy is actually being followed. So if I require this inventory to happen, then as a side effect, I know whether the things in that inventory are compliant with my policy. Another thing is a compliance artifact. So more and more compliance regulations to which we are subject talk about cryptography, and we're seeing that auditors are sort of slowly becoming more and more picky about that. So it's not enough just to say, yes, we're doing some cryptography, I'm pretty sure about that. auditors are starting to say, well, can you show me some evidence that you are following the cryptographic guidelines for PCI DSS or GLBA or whatever it is. So a crypto inventory can also be seen as a compliance artifact, something that helps you get through that compliance process in a more efficient way and make sure you actually do get through it. And finally, we can see it as a step towards crypto agility. So another driving reason to have a crypto inventory is this idea that moving forward, I might want to change my cryptography. And I might even want to change it in a hurry. So I might hear about some break, or there might be some quick change in compliance around a particular cipher, and I might want to know exactly where it is so I can change it quickly. So these are all sort of different ways to look at what a crypto inventory is. So let's drill down on these a little bit. So the sort of physical interpretation, so a map of cryptography in the organization. So you can think of it as what cryptography is used by which applications for what purpose. So it's not just a kind of a shopping list. You know, I've got some AES. It's more detailed than that. It means I've got some AES in this application, and it's used to protect customer identifying data or whatever it is. But beyond that, the level of detail that we have to go to is very much a kind of an open question, right? So we've seen people interpret that very differently. And I'll talk a little bit about some reference documents that exist, but they have very different opinions about what level of detail should go in there. So one of the things we're going to discuss a little bit today is the sort of trade-offs around that, right? So if I decide that I really want every possible detail about my cryptography to be in my inventory, what do I win from that? What gain do I get in terms of better risk management or easier compliance or whatever it is, versus what's the extra cost of actually trying to obtain that information about every single use of cryptography throughout my organization. And so as I listed here, it's not just about technical things as well. So I might want to have in my inventory somewhere where I remember that what is the business purpose of doing this encryption? So is it to meet a compliance requirement? Is it for a particular risk? And then things like who is the person I need to contact if I want to change the cryptography in that application? So a well-designed inventory can have these quite practical details involved as well. And we'll talk about all this stuff a little bit more later. Yeah, so I mentioned that you can also see it as a strategic asset in your cybersecurity posture. So a good inventory can definitely aid incident response. So one of our customers who isn't in the room today but has a very advanced crypto inventory project, and part of that is motivated by a key compromise incident that they went through a number of years ago. And it turns out that if you discover that an important cryptographic key is compromised, knowing exactly where it's stored, used, where the backups are, where the sort of replication, disaster recovery and all this kind of stuff is that's dependent on that key, can be very critical for getting an efficient incident response. So that's another sort of strategic reason why you might want to have an inventory and something to bear in mind when you think about what information that actually is going to be stored in there. So there's the aspect of incident response. So something bad has happened, how fast can I respond? Do I get some value from having this inventory, or do I have to go back and speak to everybody anyway, so maybe it doesn't help? Another way is to say, does it help me with moving proactively? So before there's an incident, I hear that, SHA-1, let's say I read the first results, I realized they were going to, SHA-1 hash function is going to be broken. So rather than waiting until somebody's screaming at me to replace SHA-1, I start phasing out SHA-1, and then I can monitor progress and see how that's going using my inventory and know where it's still being used. So this crypto agility thing, so I really, I'm not a massive fan of these sort of buzzwords that sort of come out of IT analysts and so on, but so let's look at this for what it's worth. Is there something interesting in here? So crypto agility is, so this is a Wikipedia definition, it's the idea that an information security system can switch to alternative cryptographic primitives and algorithms without making significant changes to the system's infrastructure. So the idea is that somehow you decouple the choice of algorithms and maybe key lengths from the way the application runs. So there's nothing fundamentally linked to those algorithms inside the application. So that if somebody says, okay, you need to switch from SHA-1 to SHA-256, it's somehow easy. It doesn't involve big code changes or wire format changes or infrastructure changes. So where's the kind of buzz around this come from? So some of it comes from this post-quantum report from NIST that essentially says, okay, there's going to be a change to post-quantum cryptography, but we're not ready yet, so you should try and be crypto-agile. And how do you get crypto-agile? Well, the first thing to do is know which crypto algorithms you already have. So the inventory is kind of first step towards that. And in particular, when I do inventory, I could decide to look for barriers to crypto agility. So does my application hard code algorithms? Does it hard code key lengths? Does it maybe even hard code keys? So that can be another sort of angle to why I do my inventory exercise. Right, so that's the sort of way of looking at inventory, what it is. Let's look at a few kind of driving reasons that you might have to have one. So one of them is just purely around cyber risk. So is there any real gain in having a crypto inventory in terms of reducing the risk of a breach? What kind of things would I have to have in my inventory for that to be useful for that reason? Not just a kind of box ticking exercise. What kind of compliance goals could I meet automatically or in a more efficient way if I have an inventory that's up to date? Also look at a little bit around motivations from cloud migration. So could a crypto inventory help with that? So this is from some questions that have come back from you guys. And then we'll talk a bit about post-quantum crypto preparation. Right, so at a high level, cryptography is a risk control technology, right? So it's that we have in our institution lots of ways of controlling risk, and encrypting data or whatever it is, or controlling access via cryptography is just another way to manage risk. But there's also a risk around using cryptography. So cryptography can also sometimes be a bit of a kind of comfort blanket. So it's okay, my data is encrypted. Said, capital 1, and then their data leaked out. So, and it really was encrypted on the Amazon server, right? But the way that the crypto was being applied was such that somebody who had access to that bucket could just get Amazon to do the decryption. So, it can sometimes give us a sort of false sense of security. So crypto risk is the risk that something doesn't work as well as it should, and I thought it was all fine because I was using cryptography. So we might say, ask a question, how useful is it to do this crypto inventory exercise if my objective is to control this crypto risk? So how does cryptography actually go wrong in practice? So we're going to look at a couple of sort of real incidents involving crypto going wrong. So the first thing is that cryptography almost never goes wrong because somebody comes up with some brilliant new mathematics that breaks a cryptographic algorithm, right? So there's a sort of popular conception of cryptography that somewhere there are hackers in a chat room and they're working out how to break AES, and then they're not going to tell you, and then they're going to read all your data. But that's almost certainly not happening at all. There is some exceptions to this, and that is when there's like a sort of state-level agency involved. So there's a little example around the Flame malware that I'll talk about briefly. What normally happens is that attackers actually go around cryptography, right? So they find a way to get around the cryptography that you put in place. So what kind of errors do they actually exploit, and could our crypto inventory stop those kind of things from happening? Let's look at some exploitable crypto deployment errors. So things like storing keys in a bad way, right? So this is storing keys in the clear or in the source code or in a badly configured hardware security module. These things really do get exploited, and I'll show a couple of examples of that. Another one is bad use of good algorithms. So my cipher is a good cipher, but I use it in a bad mode or I use it in a bad way. I get some parameters wrong, and I'll give a couple of examples of that. Errors in randomness, so everyone knows that random number generation is a really core technology for cryptography. If that goes wrong, lots of things go wrong, and in practice, even though we have good random generators, this really does go wrong. Composition, so using two crypto operations that are both individually good, but I use them both, and then by some mathematical property that ends up breaking the security, or even using really weak algorithms. So it does still happen in a really, really large estate of code that there is hiding somewhere some 40-bit RC4 encryption or some single DES, even though we knew long ago that we shouldn't be using these things. So let's see if is there a way we can design our crypto inventory that can help with these kind of things. So let's see a few sort of concrete examples. So this is about key storage. So you guys are probably all familiar with these one-time password key entry fobs. So how do these things work? So you have a 6-digit code on the screen. It changes every 30 seconds or something. And what's going on in there is there's a cryptographic key and it's encrypting the clock, basically. It's a little bit more complicated than that, but that's essentially what's going on. And so the way it works for verification is on my server, I have the same key. I encrypt the clock near enough, the same to you. I give you, some sort of leeway. And if I get the same value that you do, then I know you've got that key fob in your hand. But in practice, I don't want to have a database that has millions and millions of keys in, so it works with a master key system. So there's a master key that encrypts the serial number of the device, and that gives the key that I'll put inside the device. So I can reconstruct the key for any device just by knowing its public serial number. But that means I need to store those seed values that make those master keys in a really secure way. And it turned out that the RSA company wasn't storing them in a very secure way. They were essentially storing them in a database in the clear. And so when they were attacked by a very classical phishing attack, it was an Excel sheet with a name, a redundancy program for a classic kind of spear phishing thing. Eventually, these guys traversed through the network and were able to get the seed values. It was a bit of a mess because for a while the RSA company said that the seed values hadn't been attacked, but then people started logging into Lockheed Martin and exfiltrating designs of airplanes and missiles and things, and they realized that this was what had gone on. So it was a pretty kind of high consequence breach. But notice that no crypto was broken there. So the design of the one-time password mechanism inside those devices is public. It's been reviewed by expert cryptographers, and everybody knows it's great. But yeah, so it's the key storage bit that went wrong. So in terms of good crypto used in a bad way, so this was quite a famous breach. So Sony PlayStation back in 2010. So this was about digital rights management. So the idea was that you wouldn't be able to put your own code onto the PlayStation 3. It had to be signed by a key that you bought from Sony, essentially. So Sony would sell you a signature for your game, and that way Sony could make money from licensing the right to be a developer to the device. But they were using the ECDSA signature scheme, which has a property that if you reuse the same nonce value in the signature, there's a little bit of easy mathematics you can do which calculates the value of the private key. And so they made this mistake, and this completely broke their digital rights management. So pretty kind of high consequence flaw. But we see this sort of, so again, ECDSA, nice key length, nothing wrong about that stuff. Just one parameter choice that went wrong. So maybe this would be something that we would like to check is going right in our inventory. Interaction between crypto operations. So this was an interesting one. So there occasionally we hear in the news about large amounts of money disappearing from the cash machine system. But it's not very often you get to hear about the details. So in this particular case, back it's about 10 years ago now, the case went to court, and so a lot of details came out in the court proceedings. Even you could see in the court proceedings, it's quite interesting, you could see the SQL commands that had been sent to the database to no limit certain cards so that they could get out more money out of the cards, which is kind of interesting. But there was an interesting part in the story where the attackers, who were all in Russia or Estonia, they were attacking a data center in Atlanta, Georgia. They came across a hardware security module, which is essentially cryptography. So it's a box that runs cryptography and manages keys. And they didn't know how they could get the PIN codes for some cards so that they could make a financially lucrative attack. And they looked around on a chat room and found an expert who could do that. And what they found on the hardware security module was there were too many options that were still turned on, which allowed them to create a kind of code book. So they would put in some clear text PIN codes, see what they looked like encrypted, and then match them against the real PIN codes that they saw in the network. And by doing that, I think they got about 43 pins that they watched come through, and then they basically generated magnetic stripe cards and did a worldwide cash out operation, which is the sort of standard methodology for this. You go to a country where there's only a magnetic stripe card, no chip, to make it easier. And they made about 10 million bucks from that. So that's a sort of high consequence attack, but we see this kind of error of two operations which are individually secure, but you compose together to create a problem everywhere. So doing things like encrypt and MAC with the same key, or doing signature and decryption with the same key. So panning oracle attacks. So this is an interesting example of something that goes wrong in cryptography. So there's a very widely used library that's integrated into WebLogic. It's called Prime Faces. And in 2017, there was a CVE about a padding oracle attack. So I'm not going to, today's not the right day for doing crypto training, but padding oracle is basically a way to exploit cryptography that doesn't have authentication. So when you're just doing encryption without authentication, and the attacker can manipulate the ciphertext. So that's all we need to know for now. It's a cryptographic flaw. This particular padding oracle flaw allows an attacker to inject code, essentially, and get the code executed on the server. Our tool actually found this in customer code in 2016, but it wasn't even original then. It had already been found by another pen test company a few months before. So we talked with the library guys. They patched all of this stuff in 2016. But because the CV didn't come out till 2017, and anyway, people aren't really sure. They see a sort of crypto CV, they'll be like, probably that's not really a serious one. And then actually in 2018, there was a big kind of outbreak of people doing crypto jacking. So this is where you essentially put your own code onto a server and make it mine Bitcoin for you. And sort of easy way to make money. And you can just sort of spray it around the internet, just look for hosts which are vulnerable and get your own Bitcoin stuff going on. So it's another example of how the kind of intruders who can inject cryptojacking malware are able to exploit kind of crypto flaws. And then just to finish with one where people really did break a crypto algorithm. So you've seen we've had a lot of examples of crypto exploitation, but this is the only one that we've got which is really around breaking an algorithm. So part of the reconnaissance for the Stuxnet attack, so this was where a state agency made the nuclear centrifuges in the Iranian nuclear program spin too fast, so thousands of them broke, and it set back their nuclear program perhaps by over a year. So these, by the way, are nuclear centrifuges, in case you're wondering what that picture is. Of course, these aren't the ones from Iran. This is a guy guarding them, but this is from a separate incident where a boat that was going to North Korea was stopped with a load of nuclear centrifuges on it. Anyway, so in order to install itself, the Flame malware, which is the reconnaissance malware, exploited the fact that the people who designed the attack had found a way to generate two certificates that had the same MD5 digest. In particular, they'd exploited the fact that there was a legal code update certificate in Microsoft with an MD5 digest, and this allowed them to install themselves as if they were a Windows update onto a machine. So the interesting thing about this is the timeline. So nobody knows really when the first Flame malware infection happened, but people like Kaspersky and so on have done sort of research on this and have found some samples that date back to well before it was known publicly that there were MD5 collisions. So that the first MD5 certificate that was actually sort of exploited dates from a paper in 2009. But Flame seems to have been out there and installed since well before. And then the guy who discovered the MD5 collisions is this guy, Mark Stevens. It's the same guy who discovered the attacks on the collisions on SHA-1. Whoops. So yeah, here's the guy to call if you need a hash function broken. His master's was like a break of MD5, and his PhD was like a break of SHA-1, and it's sort of his sort of thing. So he actually did some reverse engineering kind of forensics on this attack, and he was able to show that the way that the collision was created for the Flame malware was completely independent from the way that his MD5 collision was created, right? So it implied that they knew about a different way of doing this attack. It wasn't that they were following his paper. So they may have had this result long before the initial results came out publicly about. So before you have an attack on a hash function, you normally have a paper saying, I think there might be an attack on a reduced version, or I think there might be an attack in a particular case. And that's what Mark Stevens was publishing before that. But these guys didn't use that at all. So that's a really interesting sort of data point if we want to understand what are the capabilities of state-level adversaries at breaking cryptography. That shows that they're a number of years ahead in terms of exploiting these things. So when we start to see that an algorithm is there are preliminary papers or it's getting weak, maybe our crypto inventory is something we can leverage to start transitioning those things out before we actually get an incident like this and we're all running around trying to get rid of our MD5. Just for reference, so I dug through the 2018 CVEs lists. So CVEs are useful because they're public data and so on, but of course there is a certain amount of noise in there. It's not always the case that people attribute CVEs correctly to the real root cause, and sometimes there's more than one root cause. But with all these provisos, let's try and get some sort of signal out of the noise. So these are the kind of things that go wrong around cryptography that came out of CVEs in 2018. So you see things like, I started with not protecting keys or storing keys in the clear. So that's a sort of big chunk of this, right? So cryptographic issues is very vague. Almost anything can be put as a cryptographic issue. So this is sort of mostly noise, but it means that somewhere around the cryptography something is wrong. We have a lot of this stuff around not protecting the credentials, stuff around certificate validation. Actually using a weak algorithm so different things get put in there, but it's relatively small. But in total, we end up with 916 attributable CVEs, so CVEs with a CWE cause, which is about twice as many as there were last year SQL injection CVEs. So, I mean, what exactly they're getting wrong, there's a lot of noise there, but we can conclude that people are getting cryptography wrong a lot, and it's often causing problems, at least of a seriousness, to open a CV. So how could the inventory actually be useful? So supposing we wanted to detect not known CVEs, but issues similar to those kind of issues in our own code, what kind of things would we want to put in our inventory to actually mitigate those risks? So you can see that it's enough to just put in the algorithms if we want to trap attacks like Flame. So if we want to know we haven't got any MD5, it's enough just to know that, is there any MD5 here? No? Okay, that's good. But if we want to go into more detailed sort of risks, so the prime face type attacks, so again, not that exact CVE, but attacks similar to that, so padding oracle related things, then we also need to capture block cipher modes and not just the block cipher. If you want to capture things like the RSA kind of attack, so where they were storing the seed values in a bad way, then if our inventory is going to help with that, maybe it's not the inventory that helps with that, but if the inventory is going to help with that, it needs to capture key storage. So I need to know, okay, I'm using crypto there, where did the key come from? How was it stored? If I want to know about attacks like the Sony PlayStation type attack where I was misusing a good signature mode, then I need to capture not just I'm using ECDSA, but I'm using ECDSA and I'm getting a random value from here. So all of these are all parameters that we can apply to our inventory, right? To say if I put this much effort in and get this much detail, what kind of risks am I now eliminating by having those kind of things in there? Yeah, so we've seen from our sort of inbound inquiries to CryptoSense that auditors are getting more and more picky about how cryptography is used. Perhaps part of this is the incidents that we mentioned, right? So I think there's more of an understanding, a more sophisticated understanding in auditors now that it's not enough just to say that we're going to use some encryption. So we're seeing them ask not just for evidence that there is a crypto policy in the organization, but that it's actually controlled. And producing this evidence is really resource consuming and error prone. One organization we spoke to described it as hand-to-hand combat to try and get from their developers evidence that the crypto policy was really being followed. So the question is, can a crypto inventory help with this? So could it help us do more efficient compliance satisfaction around cryptography? So let's look at some crypto requirements. So PCI DSS is a standard around protecting cardholder data for users of payment networks. It applies in different ways to different actors in the payment network, depending on what they're doing. And they have a definition of what they call strong cryptography. So it says that it should be on industry tested and accepted algorithms. It's kind of vague, but it's something. Strong key lengths, a minimum 112 bits of effective key strength. Proper key management practices, so what are they? But some kind of key management practices. And then they give some examples from the time of publication, some key lengths for RSA, and this is quite specific, right? So there's actual key lengths bits. There's something that you really could control, and an auditor could potentially come in with a checklist and say, show me that your RSA keys are longer than this length, and your AES is being used, and so on. And then they refer to NIST for this. So in practice, what happens is that people essentially try and follow the NIST recommendations right now, with the exception around triple DES, because the payment network has a whole bunch of triple DES in it that is not moving anytime soon. And there's also, so PCI DSS has also started controlling TLS versions. So when when they first published the recommendation, they said you have to move to TLS 1.2. It was something very ambitious, something like June 2016. And the industry screamed because it wouldn't be possible to update all the hardware and payment terminals and so on and so far. So it was supposed to come into effect in June 2018. But the reality is that there's a lot of old TLS still out there in the payment network, and people get exceptions from their auditor based on particular programs and so on. But yeah, so we can see that this, you can imagine digging through your code trying to show that you satisfy this stuff is time consuming. If you had an up-to-date inventory that was always showing that this were the only algorithms in your code, this would be a nice artifact to use to get through that part of your PCI audit. GLBA, for example, which we mentioned earlier, is similar, except it's less specific about cryptography. It says that all customer identifying data has to be encrypted and that encryption has to be proportionate to the risk, but it's much more vague. PCI DSS is quite interesting that it's so specific about this. So what we've seen is most people fall back on the sort of this NIST reference, right? So it's like, well, look, it's the NIST reference, okay? So you can't push me further than that, and that at least gives you something, solid that you can use. So another motivation for an inventory is public cloud migration. So I was sitting in the office of the head of security and privacy at one of the big cloud service providers, and he said cryptography and key management is perhaps the biggest trust issue in convincing financial services to migrate to the cloud. Could inventory be useful for this? So if I'm going to use cloud cryptography services, at least it's important to know what my application currently does. So even if I'm going to rewrite a new cloud native version, how I protect my data in the existing application is somehow a baseline specification. So the inventory can inform those decisions about, okay, this is what I was doing there, the cloud is offering me that service, and my migration plan is every time I was doing this before, I'm going to do that with this cloud crypto service. So we're seeing kind of a use case there. But yeah, so in order for the inventory to be useful for cloud migration, it's really about key management. So it's what we just said, right? So rather than just saying like, oh yeah, I've got some AES in there, I've got some MD5, well, I hope not. I really need to understand my application needs these persistent keys to be available, right? And if I'm going to put that in the cloud, I don't want those persistent keys in the virtual machine image that's running next to all these other processes. I need to find a solution for those persistent keys that satisfies my requirements about key custody or about availability and those kind of trade-offs. So if my inventory is somehow a preparation for that, my inventory needs to talk about key storage. And the last reason, post-quantum preparation. So this is a little quote from the NIST report about post-quantum. This is from 2016, I believe, this report. It's unclear when scalable quantum computers will be available. However, in the past year or so they were talking about 2015, researchers working on building a quantum computer have estimated that it's likely a quantum computer capable of breaking 2,000-bit RSA in a matter of hours could be built by 2030 for a budget of about $1 billion. Since then, I don't think that's changed that much. So I've seen a talk at a crypto thing by the guys at Google who were researching this, and they were a little bit more optimistic, but maybe that's sort of what you would expect from the people who are really in the field. Well, optimistic from their point of view, pessimistic, I guess, from our point of view. They were sort of 2025, 2030 for this. And we had an interesting non-announcement last week where Google accidentally, or not accidentally, led a paper leak out showing that they've built a quantum computer that is capable of performing at least a task which no classical computer can do. So we can see they are really advancing towards this. When exactly that's going to happen, I don't really know. So it's going to be an interesting subject. We can talk about what assumptions we're all making about when this computer is going to be available. But the really pertinent thing about this is that with that computer in 2030, potentially I could break the use of 2,000-bit RSA that's happening today, right? So I could come back, I could record some exchanges and encryption now and say, well, this could be really useful information in 10 years' time. And then when I have my computer, break this and do something bad with it. So already I need to be thinking about, okay, what is the data that I should be protecting? What are the lifetimes and this sort of stuff? Post-quantum algorithms are not ready to deploy yet. I mean, there are some prototypes, some experimental things, but we're nowhere near mature implementations that we can really deploy and be sure will be secure. So crypto inventory is a smart way to do something now to understand what we're doing, but it shouldn't just be an inventory of where we're using asymmetric crypto, but what they're used for. So what's their criticality? Do they have to run fast in the future? Is there a storage constraint? Things that will help to inform the migration, because an interesting thing about post-quantum algorithms is there's very unlikely to be one winner like we have with AES, right? So we have AES, that's the symmetric, block cipher, that's fine. Post-quantum, there's likely to be trade-offs between storage constraints and timing, and we're probably going to want to choose different algorithms for different parts of the migration. Just a couple of quick references. So who else talks about why you should have an inventory? So Gartner particularly has a publication about preparing for post-quantum, where they recommend an inventory of algorithms and distinguishing how critical they are. So am I using this algorithm to actually do something cryptographic, or is it not really cryptographic? So this can sort of gauge, is it really important to migrate this algorithm or not? And Accenture, so they have a similar kind of report about what will happen to cryptography in the post-quantum world. And essentially, they talk about extending your enterprise asset inventory to document the use of cryptographic keys, as well as third-party vendors. I think they said this should be complete by June 2019. It was a little bit optimistic, but I'm sure they'll sell you a consultant who will come and do it for you. But yeah, so there's a bunch of references out there that you can dive into to get some sort of third-party opinions about what an inventory should look like. All right, so that's end of the session. So yeah, crypto inventory is essentially a map of how cryptography is used in an organization. We've seen that it has different kinds of values, so controlling risk, so making it less likely that I have a breach because of badly used crypto. It can help me show compliance in an efficient way as part of my story for things like GLB and PCI DSS. Can help me prepare for migration, either to the cloud or also migrating to post-quantum. And so that's given us some parameters for what an inventory might actually look like. So in the next session, we'll be a bit more interactive and we'll deep dive on a number of these questions and talk about how choice of what we actually put in the inventory affects the effort required to get it and the value that it has once we have it.